Welcome to The Explainer. All right, today we are taking a deep dive into the human heart, one layer at a time. But this isn't going to be your typical anatomy lecture just listing off terms. We're going to dig into the why behind every structure and, most importantly, how it all connects to real-world clinical practice. Let's jump right in. So the heart's this incredible muscle, right? Constantly beating. But what's stopping it from just bouncing around inside your chest? Well, to really get to the heart of the matter, we actually have to start on the outside. We're going to begin with its protective housing, the pericardium. So this is it, our first layer of defense. You can totally think of it as the heart's personal bodyguard. It might look like a simple, tough sac from the outside, but trust me, what's going on inside is way more complex. And it has some really crucial clinical applications. Okay, so it's not quite as simple as just one bag. The pericardium is actually made of two distinct layers. You've got this super tough outer layer, the fibrous pericardium. That's the anchor. It literally locks the heart in place by fusing with the big vessels and the diaphragm. Then, tucked inside, you have the serous pericardium. This one's more delicate, and it's this clever two-part layer that creates a slick, friction-free environment so the heart can beat millions of times without rubbing against anything. Pretty smart design. Now, nestled between those serous layers are these two really important spaces, or sinuses. And the transverse sinus? This is not just some random space you have to memorize for a test. This is a surgeon's secret passageway. Seriously, during open heart surgery, they can slide a clamp right through this passage to get a hold of the aorta and the pulmonary trunk. It's how they get control of the major blood flow out of the heart. Super critical. And here is a perfect aha moment for why anatomy matters. Ever wonder why pericarditis, inflammation of this sac, causes such a sharp stabbing pain? It all comes down to the wiring. That outer part of the serous layer, the parietal layer, is supplied by the phrenic nerve, and that nerve carries sharp, specific pain signals. It's totally different from the vague, crushing pain of a heart attack, which comes from the heart muscle. See? The anatomy directly explains the patient's symptoms. Okay, so we've got the heart in its protective bag. Now let's figure out how it actually sits in the chest. Because here's the thing, it doesn't sit straight up and down like you see on a Valentine's card. It's actually twisted and tilted. And getting your head around this oblique orientation is absolutely key for understanding everything else we're going to talk about. Because of that twist, what we call the right side of the heart ends up being more in the front, and the left side is more in the back. So when you look at the heart head on, what are you actually seeing? Well, that entire right edge you see, that's all right atrium. And the left edge, including that pointy bit at the bottom, the apex, that's almost entirely the powerful left ventricle. All right, time for the main event. Let's get inside and take a tour of the four chambers. And we're going to do this logically. We're just going to follow the natural path of blood, starting right where all the used up, deoxygenated blood from the body gets dropped off. And here we are, inside the right atrium. Now check out these internal landmarks. You see that vertical ridge of muscle? That's the crista terminalis. It's like a dividing line. It separates the super smooth posterior part from the rough, bumpy anterior part, which is covered in these comb-like muscles called pectinate muscles. And look right there, on the wall between the atria, that little thumbprint-sized depression? That's the fossa ovalis. It's a beautiful little remnant of a hole that existed when we were fetuses, letting blood bypass the lungs. So cool. Okay, blood flows down from the right atrium into the right ventricle. And whoa, look at these walls. They're not smooth at all. They're covered in these meaty ridges called trabeculae carneae. But the real star of the show in here is the moderator band. It looks like just another strand of muscle, but it's an ingenious electrical shortcut. It carries a piece of the heart's conduction system directly over to the outer wall, ensuring the entire ventricle contracts at the exact same time. It's an engineering marvel. Now, let's hop over to the left side of the heart. This is where all that fresh, oxygenated blood from the lungs comes pouring into the left atrium. And remember that twist we talked about? Well, this chamber actually makes up most of the very back of the heart. You'll also notice it's mainly smooth-walled, which is a neat clue to its development. It's smooth because it literally absorbed the pulmonary veins into its own wall as it grew. And our final stop is the powerhouse, the left ventricle. This slide says it all. Its walls are 3 times thicker than the right ventricles. And think about why for a second. The right ventricle just has to pump blood next door to the lungs. It's a short trip. But the left ventricle, it's got the massive job of pumping that blood to your entire body, from your brain to your toes. That requires some serious muscle. Okay, so we've got these four powerful chambers, but what gives the heart its actual structure? And what keeps blood from just sloshing backward after every pump? That brings us to the heart's internal framework and its four absolutely crucial gates, the valves.
Think of this as the heart's chassis. It's called the fibrous skeleton, and it's this incredibly strong figure-8 shaped frame made of dense tissue. It does three critical jobs. One, it provides a solid anchor for the valve cusps to attach to. Two, it's the attachment point for the heart muscle itself. And three, this is so important, it's an electrical insulator. It completely separates the atria from the ventricles, so electrical signals can only get through the proper conduction pathway. It prevents electrical chaos.
And plugged right into that fibrous skeleton are the heart's four valves. It's pretty straightforward. You've got two between the atria and the ventricles. We call them AV valves. That's the tricuspid on the right and the mitral on the left. Then you've got two more guarding the exits to the big arteries. Those are the semilunar valves, the pulmonary and the aortic. Now, this is a key concept. These two sets of valves work in completely different ways. The AV valves, the tricuspid and mitral, they close actively. Little muscles pull on these heartstrings, the chordae tendineae, to hold the valve shut so it doesn't blow backward under pressure. In contrast, the semilunar valves are totally passive. As soon as the ventricle relaxes, the back pressure of blood in the arteries just fills up their little cups and snaps them shut. It's a beautifully simple, pressure-driven system. So far, we've gone through all this pure anatomy. But what's the point? Well, this is the payoff. Now we're going to see how these details connect directly to what doctors do every single day. This is why it all matters so much. Check this out. This is anatomy in action, and it can be a matter of life and death. If fluid builds up in that pericardial sac and starts to crush the heart, you have to drain it. But you can't just guess where to stick the needle. You follow this very specific path between the xiphoid process and the ribs, angling up toward the left shoulder. Why? Because the anatomy tells you that's the safe corridor that avoids the lungs and liver. This is life-saving anatomy, plain and simple. Here's another classic example. When listening to the heart, you'd think you'd just put the stethoscope right over the valve, right? Nope. You actually listen downstream, where the sound of the valve slamming shut is carried by the flow of blood and is loudest against the chest wall. That's why you listen for the aortic valve over on the right side of the sternum, and for the mitral valve way out at the apex. It's all about following the flow of blood. So as we've seen, from a single nerve explaining a patient's specific type of pain to an exact path that guides a surgeon's needle, it's clear, isn't it? Every border, every sinus, every layer of the heart isn't just a fact to be memorized. It's a fundamental chapter in the instruction manual for understanding, diagnosing, and ultimately treating the human body.